Okay, question 16 says a natural gas production in Norway has been increasing with the development of North Sea projects. So what this is measuring the amount of natural gas that's being produced per year. The very first thing we'd have to do in order to get an idea of this is figure out which is the independent variable and which is the dependent variable. So, Sampras, which is it? Year is what? That's right. So if years are independent variable, which makes production our dependent variable, which goes on the x and which goes on the y-axis? Ask everybody. Ask everybody. Your independent variable always goes on the x-axis. Okay? So that means in order for us to figure out a regression model from our three formulas here, we have linear, quadratic, or exponential. We know this will be our x-axis, this will be our y. We're going to have to use our first, second differences and our decay and growth models in order to figure this out. Now, am I able to run those tests by looking at our x variables? Why can't I run it? How do you know? Yes. So they consistently go up by the same number, which means we can run those tests on our y variable, which is production. Okay? So I'm going to put another chart below, and we're going to run the three tests. So we have our y as our dependent variable, which is production of natural gas. We need to figure out, first of all, if this is linear. So what do I need to do? Good. You sound so excited. All right, so we need to find the first differences of our y variable. So for our first differences, we'll take the top number and subtract the next one down. 43 subtract 48 is negative 5. 48 subtract 57. It's going to give us negative 9. 57 subtract 64. Is that negative 5 again? No. Negative 8. And 64 subtract 76 is negative 12. Are all the first differences the same? No. So is this a linear relationship? Not linear. All right, our next model to figure out if it's quadratic, we have to take the differences of the first differences. So our second differences, negative 5 from negative 9. Negative 5 subtract negative 9. Anybody know off the top of their head what that is? 4. Positive 4. Good. Negative 9 subtract negative 8. Negative 1. Good. Negative 8 subtract negative 12. Yeah, Ramel? Sorry, let's fix this number. That's negative 7. That changes this to negative 7, which means our answer is negative 2. Let's clean this up a little. And finally, positive 4. Are our second differences the same? We have negative 4, negative 2, and negative 4. Are the second differences the same at all? No. So, this is not quadratic either. Oh, we'll see if it is. Okay, we'll look at... Now, we got to figure out if this is a growth or a decay when we're testing it. 2, 3, 4, 1, 2, 3, 4. Is production going up or down? The numbers are constantly increasing, so is this a decay or would this be growth? Growth, good. So we're talking about exponential growth. We'll divide the two. 43 by 48. .895 or 0.89. Should have made more room for this. 48 divide 57. .84. It's not bad, it's close. .57 divides 64. 0.89, that's 0.84. Sorry guys, that should have gave us more room. And finally, 64 divided by 76. 0.84. How about our exponential model? Are they all the same? They're roughly the same. They're only off by 1/100th. That's close enough for our regression model. We have 0.89, 0.84, 0.89, and 0.84. This will be closest to to an exponential growth. It definitely was not linear, and it wasn't quadratic. So their best regression model for this is exponential growth. And another way we could test this out is by actually plotting it on a graph to see if this makes sense, if it looks like an exponential graph. So on the next page, we're going to plot these all as points. Okay, so we were taking this up yesterday. So we have our data, and we know that these are all going to be coordinates. So we're going to have, what is it, 6? No, 5. We have 5 coordinates we can plot. Now, we actually have to make our graph. We have to put what the range of this graph is going to be. So if we take a look at our x-axis, it goes from the number 2000 to 2004. What I'm going to do is I'm going to make each of these grid panels go up by 1 year. So remember, we're going to have to always start at 0 our graph, and we use that broken line to say that we're skipping a large amount of data. We go up to the number 2000, then 2001, 2002, 2003, 2004, and 2005. Now, the reason I've made this graph go much farther is because in our next question, they're going to ask us to extrapolate data. They want to know, they want us to predict in the future how high something's going to be. So I decided to let this graph go up to 2010 so I can better predict this. So that was the range of our x-axis, which were the years. Our y-axis is production. Production goes from 43 to 76, so it has a range of 33. Now, if I'm going to be predicting to 2010 roughly, the end of this graph, and it's exponential, that means it's going to grow very quickly. So instead, I'm going to make my y column go in tens. So we're 10, 20, and hopefully our graph will be able to predict with it a relatively good estimate. Okay, so we're going to plot the 6 points we do have. In the year 2000, we're at 43. So, because we have to predict very far. If it's exponential, that means it's going to grow quicker and quicker every year. And I said we have to extrapolate data. So if you look at the next question, they're asking us, where do we think it will be in 2010? So if it's exponential growth, it's going to grow a lot. So if I only go up by 5s, my graph down here, I won't be able to cover all the data. I want to try to be close. So I gave it a larger range. But you're right, that would be more accurate. Okay, so we have 2043 was our first point. Our second point in year 2001 is 48. 2002 is 57. 2003 is 64. 2004 is 76. If we look at this, this actually ends up looking quite flat. But what's going to end up happening is eventually this is going to start to take off more and more. So unfortunately, even my y-axis isn't going to give me a good estimate to 2010. Okay? So if the ratio, now what we're going to do to extrapolate the data, we're predicting when the natural gas production in Norway, or what it will be in 2010. Okay? Now I could look at the graph, but it'll be very hard to get an accurate number here. So I actually have to go back to my ratios from before. So remember, we're going to say that this ratio was 0.89 in hours over here. And that's because we divided the first number by the second number. Okay? Now, what I want you guys to figure out is I can actually use math to extrapolate this data. There is a growth pattern. This is being multiplied by a certain number every time. In order to figure out that number, because it's growth, this is very important because you'll have something like this on your test. Because it's growth, you need to divide the larger number by the smaller number to find out what the ratio is for growth. So I'm going to take the number 48 and divide it by 43. 48 divided by 43 equals 1.16. Another way I could have figured that out is if I took the ratio we found before and we divided that by 1. So if I had taken this ratio and I had 1 divided by this, 1 divided by 0.89, oh, 1.23. It's a little off. What do we got, 1.23? So whether you decide to find the ratio this way or you decide to take our first numbers here, we're relatively close because we're trying to extrapolate data now. So what that means is every year, whatever the number is the year before, we're going to be multiplying by this. This is our factor of growth. So we'll go over to our graph page. In 2004, we were at 76. If I multiply that by our factor, 1.16, I'm going to get for the year 2005 what it's predicted the gas growth will be. So we take 76, multiply by 1.16, roughly going to be 88 in that year. I'm going to have to continue this pattern to get to 2010. We're going to continuously have to multiply by our growth factor. $1.16. This is what we discovered our growth factor was going to be. Oh, did I have it? So I clearly read the calculator wrong. This is 1.116 and this was 1.12. These numbers are far more similar, okay? We can round them to 1.1. So I'm going to go back to our other page and just correct that quickly. Luckily, we only made one calculation. We're going to use a growth factor of 1.1. We're just going to round it to the tens column, okay? So 1.1 will be our growth factor for all of this. This is a good estimate. You could go farther. The farther or the larger your decimal, the more accurate your number will be. But if you go to the 10th column, it'll be a good estimation. Because remember, we're estimating. It's not guaranteed it's going to be this every year, so we want to be conservative. So when we multiply that 76 by 1.1, oops. 83.6 in our next year. So we'll fix that. Now, remember, because we want to get to 2010, I could write down all the numbers, and that'll help me a lot in case I make a mistake along the way. But I know I can just quickly multiply by 1.1 every single time. Oh, it's supposed to be 83.6. I'm really having trouble writing numbers down today. Okay. If we multiply by 1.1 again, that's 2006, 2007, 2008, 2009, and in the year 2010, it looks like their gas production is going to be 134.6 for that year. So a coordinate for the year 2010 be 2010 and 134.6 in terms of our gas. We'd have to use the same idea to again predict for the year 2020. We would multiply by our growth factor again to get a number for that year.